Magandang araw, MatE 21 class. Ngayon, ang ating pag-aaralan ay ang thermal properties ng ating mga materyales. So, ano nga ba ang thermal property natin? Ang thermal property ay ito ang response ng inyong material sa application of heat. When ang isang solid ay nag-absorb ng heat, pwedeng tumaas ang kanyang temperature, pwedeng lumaki ang kanyang dimensions or ang kanyang laki, at pwede ring magkaroon tayo ng tinatawag na thermal conduction in which lumilipat yung init mula sa mainit na lugar papunta sa malamig na lugar. Una, tingnan natin ang tinatawag nating heat capacity. Heat capacity is represented by the letter C. This is the ability of a material to absorb heat from the external surroundings. We measure this per temperature. So this is the amount of heat or energy needed to raise the temperature of that material a degree higher. Mathematically, it can be expressed using the following equation. C is equal to dq over dt, or dq is the change in energy or heat, and dt is the change in temperature. Makita natin na pag mas taas yung change in energy natin bago tumaas yung temperature mo ng 1 degree, mas mataas yung heat capacity mo. This is usually specified per mole of a material, joules per mole Kelvin. Habang dinadagdagan natin ng heat ang material natin, nakita natin that magva-vibrate yung atoms natin in their lattice position. So itong vibration ng lattice position ng vibration ng atoms natin in their lattice position, this will create waves in your lattice. Itong waves na to, tinatawag natin tong phonons. So yung phonons natin, these are quantum mechanical particles representing the vibration of your lattice. Given that, yung phonon natin, this can only be created by the collective motion of the atoms. Hindi lang isang atom yung pwede mag-produce sa kanya. And also, the heat capacity of your material then will be related to the ease of which our phonons are created. Specifically, pag mas madaling mag-form yung phonons natin, bababa yung heat capacity mo. Since essentially, mas konting energy ang kailangan mo ipasok sa material mo para mag-create ng bagong phonon mode, ibig sabihin, mas madaling tataas yung temperatura nung iyong material. Looking at the temperature dependence of heat capacity, we can see that as temperature increases, your heat capacity increases. At low temperatures, we can see that your heat capacity here can be fit to this formula. CV is equal to A T cube. Or ibig sabihin yan, your heat capacity is related to the cube or is proportional to the cube of your temperature. But this only happens at really low temperatures. It's less than around 50 Kelvin. Then, after that point, makita natin mag-slow down yung increase ng heat capacity natin until it approximates the value 3R. So, itong 3R na to, nakita to dati ni Dulong and Petit. So, meron silang tinatawag na Dulong-Petit law. And at the temperature in which tinitingnan natin kung saan nagsisimula to, we can define this as your Debye temperature. So, after the Debye temperature, magkakaroon tayo ng idea na medyo nagko-constant na yung heat capacity ng material natin. And it would approximate the value 3R as proposed by Dulong and Petit. So, makita natin this relationship for your heat capacity and temperature is followed by a lot of our, most of our materials. So, we have here, this is lead, copper, aluminum, and carbon. So, makita natin you have the increase in your heat capacity. Then, asymptotic siya with 3R. So, yung sa carbon, yung Debye temperature niya is nandito pa. Hindi pa siya nag-asymptotic. But, as you increase in temperature, makita natin, mag-approximate din yan with 3R. Now, let's look at the coefficient of thermal expansion, alpha. So alpha is the measure of the amount of which a material's length or volume increases when your temperature is increased. Mathematically, we can define alpha using the following formulas. So yung alpha natin dito, alpha, this will be equal to delta L over L naught over delta T, or delta L over L naught is equal to alpha L delta T, where delta L is change in length, L naught is the original length, and delta T is a change in temperature. We can also define this for volume. Delta V over V naught is equal to alpha V over delta T. So makita natin dito that if your length, if mataas yung increase ng length natin with respect to delta T, your alpha will be high. But if delta T is high but the change in length is low, or maliit lang yung change in length natin with increase in temperature, makita natin that your alpha L would be low, or it would not expand as much upon application of heat. Note though, for most materials, your alpha, your coefficient of thermal expansion, is anisotropic. This means that depende sa direction, magkakaiba yung expansion natin. So this has something to do with the crystal structures of our materials. So for your materials, the one that will determine whether or not your coefficient of thermal expansion would be high or low is the potential energy curve of your material. So recall from our first lessons in MatE 21, nasa classroom pa tayo, the potential energy can be plotted against the interatomic distance of your material. So tinitingnan natin dito is the CTE of a material depends on the symmetry or the asymmetry of this curve here. If your curve, depending on whether or not your curve is more symmetric or more asymmetric, will determine whether or not mataas or mababa ang coefficient of thermal expansion niya. Generally, the deeper the curve becomes, the stronger the bond and the more symmetric your well is. If your symmetry is high, ine-expect natin that the coefficient of thermal expansion would be low. Looking at these two curves here, let's look at this one first. For this one, this is your potential energy versus interatomic distance curve. At 0 Kelvin, yung energy ng material mo is at the bottom of the well. It is here. If we increase the temperature, let's say to T3 here, if we increase the temperature into here, yung curve natin, eto na siya. Dito na tayo tumatama. And this curve actually gives you the bound in which kung saan pwede gumalaw yung atom natin na ito in relation to the other atom. So this is atom 1 and atom 2. So pwede siya mag-oscillate ng position from here to here. And yung magiging mean position niya or average position niya would be somewhere here. So if more asymmetric yung curve natin, makita natin, let's say, for an increase of temperature na ganito kalaki, yung change nung bond length natin from dito, let's say, gamitin natin yung blue. So, at 0 Kelvin, ganito yung bond length mo. At an increase in temperature, delta T, na ganito, makita natin that your bond length would be ganito na. Masyado na siyang mahaba. Malaki na yung increase in the length of our bond, the average length of our bond. Malaki na yung increase in the dimension of our material with increase in temperature. Contrast that with a solid with a strong bond. So, pag strong yung bond mo, let's say we have the same length, ganito, mula dito sa ilalim, pataas, dito ka lang tatama. So, initially, yung bond length niya is ganyan. But as we increase with the temperature delta T dito, yung change in the average position of your atom 2 with respect to atom 1, maliit lang yung difference. Kumpara dun sa isa, makita natin mas maliit yung thermal expansion niya with the same amount of increase in temperature. Mas mababa yung coefficient of thermal expansion for a more stronger bond material, so for a strongly bonded material than a weakly bonded material. So for thermal expansion, if you increase the bond energy or the curve symmetry, the coefficient of thermal expansion of that material would decrease. Looking at your materials, alam natin that your strongest na bond strength is usually sa ceramics. So for ceramics, strongest bond strength, then metals, then polymers is bond strength. So if we look at coefficient of thermal expansion, so for coefficient of thermal expansion, alpha, makita natin that your ceramics would have the least CTE, followed by your metals, then lastly sa polymers natin, readily nag-expand sila upon increase in temperature. So lastly, we look at thermal conductivity. So the thermal conductivity is the rate at which heat flows through our material. This is the measure of the ability of a material to conduct heat. So this is important in different applications since sometimes gusto natin mataas yung conductivity natin, such as in your frying pans and so on. And sometimes gusto mo insulating naman yung material mo in the case of like insulation and so on. So your thermal conductivity mathematically when expressed thus at Q is equal to negative K dt over dx. Yung K natin dito, this is your thermal conductivity. Q is what we call heat flux. And dt over dx is the change in temperature with the change in distance from the heat source. So for our heat conduction, you have two primary mechanisms in which heat can transfer from one point to another. We have electronic and phonon heat conduction. So from the name, yung electronic heat conduction natin is through the action of our free or valence electrons, while phonon heat conduction is through the action of our lattice vibrations or our phonons. Looking at our metals, yung thermal conductivity niya, this is dominated by your electronic heat conduction. Because recall sa metals natin, naka-embed nga siya in a sea of electrons, yung atoms mo. That sea of electrons is actually collection of free or valence electrons moving around your lattice, and this facilitates your heat conduction. Given that the primary conduction of heat in metals happen through the movement of electrons, makita natin that your heat conduction would be hindered when your electrons faces obstacles or they are scattered inside their path. So compare two different electrons, one with no scattering and one with scattering, to get from point A to point B, the one with no scattering would be faster than the one that is scattered. Which would mean na pag tumaas yung scattering events natin or mas marami tayong scattering centers in your solid, mas mabagal yung heat conduction ng ating material. So yung scattering centers natin na yan, this can be a lot of things. Pwede yan different electrons, it can be discontinuities in your metal, grain boundaries, impurities, and so on. Next, let's look at thermal conductivity of ceramics. So thermal conductivity of ceramics, unlike your metals, this is dominated by phonon heat conduction since there is very low amount of free electrons in your ceramics. Kasi nga, yung electrons natin yung valence electrons sa ceramics, usually involve siya in the bonding. Thus, yung thermal conductivity of ceramics natin, this is sensitive to the presence of pores or voids in your material. So, yung pores and voids natin, this is usually made of air or gas or vacuum. And these substances are good insulators. And their presence in the material would lower the conductivity of our ceramics. So for ceramics, yung thermal conductivity nila nagbe-vary in a wide range. On one hand, we have ceramics like diamond. In diamonds, the transfer of phonons or vibrations from one point to the other is very efficient due to its crystal structure. This results in a very high thermal conductivity of diamond, which is about 5 to 6 times higher than copper, which is in itself a very good thermal conductor already. On the other side of the spectrum, we have ceramics that are very porous. So shown here, this is aerogel. So yung aerogel mo, this is about 99% air. So 99% void sa structure niya, and due to these voids, mabagal yung heat transmission from one point to another. Kaya pwede niya pa rin hawakan yung aerogel natin kahit sinusunog mo na yung taas. Amazing! So for polymers, similar to our ceramics, wala siyang masyadong free electrons. So we expect that vibration or our phonons would be the main culprit for the propagation of heat from one point to another. Sa polymers natin, yung structure niya is amorphous generally. And this makes it hard for your phonons to get from point A to point B since hindi masyadong ma-coordinate yung vibration from one point to another. So, if we increase the crystallinity of our polymer, ina-expect natin na mas i-increase yung conductivity ng polymer mo when compared to a polymer of the same structure which is now amorphous. So, in general, for polymers, if you increase the crystallinity or the order in which our polymers are placed in their structure, the thermal conductivity of our polymers would increase. So now that we know about heat capacity, coefficient of thermal expansion, and thermal conductivity, we can rank which among the three monolithic materials would have, let's say, the highest and lowest heat capacity. So for heat capacity, yung pinaka-lowest natin is yung sa metals mo, then followed by ceramics, then lastly, polymers. Since sa heat capacity mo, your heat capacity is dictated by the ease in phonon creation, and the ease of phonon creation is usually related to the structure of your metal or your material, kung mas madali bang mag-coordinate yung atoms more, hindi. So metals usually have the simplest structures, mas madali tayong gumawa ng phonon, and habang mas complex yung structure mo, mas mahirap gumawa ng phonon. Sa polymers mo, medyo complex yung structure mo, nahihirapan na gumawa ng phonon, tumataas ang kanyang heat capacity. For coefficient of thermal expansion, we see that your coefficient of thermal expansion is related to the depth of the potential energy curve or the potential energy well or the bond strength of your material. So looking at that, your polymers have the lowest bond strength. They would have the highest coefficient of thermal expansion, followed by your metals, then your ceramics. And for thermal conductivity, establish that your metals have the highest, generally, high, your ceramics, there's siyang high or low, and for polymers, usually, mababa yung thermal conductivity nila. So now let's look at thermal stress. So, your material, upon application of heat, makita natin na mag-i-increase yung kanyang dimensions. But when your material is constrained to a specific dimension, instead of expanding kasi wala nga siya pupuntahan, magde-develop ka ng internal stress in your material. So this stress, sigma, the thermal stress sigma, this will be related to E, your Young's modulus, alpha L, which is your coefficient of thermal expansion, and delta T, or the temperature difference between the initial and the final state. So if we increase the stiffness and the coefficient of thermal expansion of your material, makita natin mas mataas yung thermal stress na ma-experience yung material mo. And if your thermal stress sumobra siya sa isang threshold na stress natin, pwedeng mag-fail yung material mo. Your thermal stresses can also arise from temperature gradients during heating and cooling. Because when you're heating or cooling a material, hindi naman uniform yung pagtaas and pagbaba nung heat or ng temperature ng material mo. Naglalag usually yung center ng material mo dun sa surface when you're heating or cooling your material, and this difference in the thermal stress would cause different dimensions in your material, which might cause cracking or thermal stresses to develop within the material. So we usually study thermal stresses since your thermal stress can be a point of failure of your material. So one such failure is thermal shock. Thermal shock happens when a ceramic is rapidly heated or cooled. So this rapid heating or cooling of your ceramic would cause high thermal stresses within your material. Since makita natin that your ceramics are usually low in thermal conductivity. So, pag mataas nag-heat yung surface mo, baka yung loob malamig pa rin. And this difference in your temperature will cause internal thermal stresses in your material, which might cause cracking to occur. So, itong thermal shock natin, nakita natin yan when you heat up glass pieces very fast or and so on, yung makita nyo lang, bigla na lang magka-crack yung material mo. So, example, itong paso, pag iniinit mo, yung loob malamig, yung labas mainit, di kaya ng material mo withstand yung thermal stress, and since ceramic, usually brittle yan, instead of plastically deforming, they will just crack. So, your thermal shock resistance, this is a quantity that predicts, or this is a figure of merit that looks at how resistant your material is to failing via thermal shock. So thermal shock resistance increases with increase in the fracture strength of your material and the thermal conductivity of your material, and it decreases with your stiffness or your Young's modulus and your alpha L or coefficient of thermal expansion. So with that, I end our lecture for today. So thank you, God bless, and hope you are all staying safe and sane in these times. Thank you. Bye-bye.